Okay, so the next topic that we covered was earthquakes. And earthquakes obviously are related to faults. And so we started with a short review of fault types. We talked about these high angle, normal and reverse faults where the what we call the hanging block, that's the one that if you were a miner right down in here on the fault, this would be the foot block and this would be the hanging block or the hanging wall, with the fault plane oriented that way. A normal fault is one where the hanging wall is moving downward. A reverse fault or a thrust fault is one where the hanging wall is moving up over the other material. And then we have, of course, these strike-slip faults where material is just moving past one another. All three of these fault types are capable of producing earthquakes, and they do. The magnitudes and styles of earthquakes differ slightly, but they all produce similar effects. And in general, those effects are captured by seismic waves. And so there are really four different types of seismic waves that we discussed. Two of them are what we call body waves, and that's just to say that they travel through material. And two of them are surface waves, meaning that they just travel at the surface. The two types of body waves, or internal waves, are shear waves and pressure waves. And we call them P and S, which conveniently are the same first letters as shear and pressure, but realistically those refer to primary and secondary waves, and that refers to their arrival time, and really the speed at which they travel through materials or earth materials. Okay, and so a P wave is the primary wave. It's the first that arrives, and it's a compressional wave. And so this animation just shows, if you push real hard on this side of this block, it compresses, and that compressed area travels, it propagates forward through that material. It's very analogous to sound. Sound waves are compressional waves traveling through air. Okay, shear waves are different. Shear waves, the particle motion is perpendicular to the direction of propagation, and so this shows a shear wave, and you can see that the particle motion is up and down, whereas the direction of propagation is to the right. Okay, and this type of wave, propagating this type of wave, requires the material to have shear strength, which we talked about liquids and fluids in general, so air or gas or a liquid, does not have shear strength, right? So you can take a spring, right, and go like this, and the wave will propagate. But if you have a bunch of water in an aquarium and you lift up one side, it's not going to propagate the same way. It might create a surface wave because the water's sloshing around, but in general, shear waves are not capable of traveling through fluids because fluids don't have shear strength. Okay, and so primary waves and secondary waves, or pressure waves and shear waves, travel through a material, through the interior of the earth. Surface waves are different. They travel at the surface, and so there are two types, Rayleigh waves and Love waves. Rayleigh waves are characterized by kind of an up and down wave motion, but if you look at an individual particle or one of these cubes, what you'd find is that the motion is actually circular, and it's retrograde, we would say, to the direction of propagation. And so each one of these blocks moves kind of forward, up, backward, and then down as this wave propagates. It's very similar to the way an ocean wave propagates, right? And what we learned when we talked about ocean waves is that they don't go all the way down to the bottom of the ocean, right? There is a maximum depth that their energy propagates to. They travel exclusively at the surface of the ocean, right? The second type is a Love wave. It's similar, but it's similar but different. It travels at the surface. Like a shear wave, the particle motion is actually perpendicular to the direction of propagation. So in this case, with Love waves, particle motion goes back and forth, sideways. And we saw an example of this in a video that we watched in class, where the buildings in the background were swaying a lot. And the buildings in the foreground, or foreground, background. So the buildings in the background were moving a lot like that, right? That's the propagation of a Love wave, shaking the earth side to side. Okay, so we talked about how we can use these different waves to calculate the focus point and the epicenter of an earthquake. We can do that because they arrive at different times. The pressure wave or the primary wave travels faster than the shear wave or the secondary wave. And so if we have a single seismogram or seismograph, it'll produce a seismogram like this. The P wave will arrive, sometime later the S wave, and then the surface waves will arrive after that. And if we know the relative travel times of these, which we generally do, by measuring the difference in time of their arrivals, we're able to calculate a distance away from the origin of the earthquake. And so using multiple different stations, 3 or more, we're able to uniquely triangulate a single epicenter for the earthquake. This is, of course, done in three dimensions, and so what you would really be calculating is the focus point rather than the epicenter. Okay, so moving forward through this, we've got the types of seismic waves and how we use them to understand the location and propagation of earthquakes. We also use those seismic waves to understand the Earth's interior. We talked about, where is that slide? It was an animation here. We talked about it in reference to understanding the liquid nature of the outer core, right? Shear waves will not propagate through the outer core because it's liquid, and shear waves require shear strength to propagate, which liquids do not have. Okay, we moved forward and we talked a little bit about recurrence intervals. The take-home message here is that very, very large earthquakes don't happen very often, maybe once a year or once every few years, whereas very small earthquakes happen almost continuously. But all earthquakes happen as a result of strain, right, that results from the stress field that's produced by plate tectonics, mostly, and other factors, but largely due to plate tectonics. Okay. We talked about a couple of other things, subsidence and uplift, ground shaking. There is in particular an example from the Cascadia subduction zone. If I can find it, that's the New Madrid. Gosh. I don't see the slide I'm looking for, but in general, during these events, you can have ground motion, and so ground can go up, ground can go down. Before these events, leading up to them, there can be a lot of flexure, a lot of sort of we would say elastic deformation, right? And so the plates move as they strain in response to this stress. But the earthquake occurs when the fault slips and a lot of that elastic energy is released. And so you can see this very clearly in places like subduction zones where, wish I could find the slide that I'm looking for here. That's ground shaking. That's New Zealand. Oh, here we go. Okay, so the Cascadia subduction zone is a subduction zone. The Cascade Range is a volcanic arc that is related to melting of the Juan de Fuca plate as it's being subducted beneath North America. But what happens in a subduction zone, and this is true of the Cascadian subduction zone, it would be true of Japan. So this is showing Japan in particular. But what happens is that as the plate goes underneath, it pushes the overriding plate back, and that causes it to flex and bulge upward, right, as it gets pushed back. But eventually there's so much elastic strain here and so much related force pushing back, trying to relax that back to its initial position, that an earthquake occurs. Rupture along this fault plane occurs, and it allows the overriding plate to slip back forward. This causes the ground surface to subside back to its original position or thereabouts, and it can create large tsunamis in the process. That's really the last point I wanted to make on this, and I will move on. The next video will be on weathering and erosion.